All right, welcome back. In this video, we're going to tackle a couple more difficult examples of finding volumes by slicing. In this example right here, what we're doing is we're going to take the region that's bound by y equals x cubed and the square root of x, and then we're going to rotate it about y equals 1. A crucial difference here from the other examples is we're not taking one of the axes to do this rotation. We're going to rotate it against this horizontal line y equals 1. And as you've seen in the previous videos, it's a bit difficult to represent and to show you graphically what these solids of rotation actually look like. And so what I want to do right now is, before we get going with this graphical representation and doing the dirty work, I want to look at a computer generated graphic of what this object actually looks like. So we'll stop it right there. I want to leave a little bit gap there because I think it kind of illustrates what it looks like. But importantly, that's that object. And again, you'll notice we're not actually rotating around the x-axis, though we are rotating along this horizontal line. This will actually give us these slices that have this delta x. And in this case too, as you'll notice, that we have these gaps in the slices, we'll be using the washer method to attack this. Given that we just had a beautiful computer-generated graphic of this, I'm not going to try to represent that same thing here, but I will attack this and look at these little washer pieces. So importantly, let's choose some value here just on this interval. By the way, this region is from 0 to 1 in both the x and the y axis right here. But in this case, what we're going to do is we're going to take this little washer, and the washer comes from rotating this around and rotating this around. As in the previous example, when we were dealing with these little washers, we don't have these solid discs. We have these gaps when we're finding these areas. What we need to do is identify this inner radius right here. Importantly, you'll see that's the difference between the square root of x and 1. And then we have an outer radius, which is the difference in length here between y equals 1 and the x cubed. So after other examples, we showed this kind of more formulaic process for attacking these. This is a washer method right here because we have this gap in the middle where we won't have any volume. But our formula generally is this pi times the outer radius squared, and I'll just write r sub o squared, minus pi times the inner radius squared. So the only work we really have to do is find expressions for these inner and outer radius. Again, we're looking to do this in terms of x, and in this case, because we have these vertically standing washers that we're looking at along the x-axis that have this width of delta x. So let's attack this outer radius first. So the outer radius is the distance here between a y value of 1 and this curve y equals x cubed. So the outer radius, we'll just do 1 minus x cubed. And then for the inner radius, we're looking for the difference between 1 right here and the square root of x. And so we can simply do 1 minus the square root of x. So that's the real analytical work. Now I'm just going to clean this up and combine any like terms and make it a nice expression here. And so when I do this, the first thing I'm going to do, and you can always do, is factor out this pi that's in both of those terms. When I expand this out, I get 1 minus 2x cubed plus x to the 6th. When I expand this out, I may make sure I subtract this from everything. So this is a 1 minus 2 square root of x plus square root of x times the square root of x is just x. Then distributing this negative to all of these terms, that's the one thing to make sure that you do here to not make a mistake. What I'll get here is that the area is pi times, let's go in order here. So I have an x to the 6th. Minus 2x cubes, so those are gone. I have a minus x right here. I now have a plus 2 square root of x. I'm going to write that as x to the 1/2 just because I know I'm going to integrate. It makes my life easier. And then I got a positive 1 and a negative 1, so those cancel out right there. So there I have my cross-sectional areas described by this right here. The only other thing I need are my bounds, and I see, well, they meet here at 0, obviously, they go to 1. So I'm going to integrate based on these x's, these delta x. I'm going to integrate from 0 to 1 this cross-sectional area. And so then here when I'm doing this, I just pulled out this factor of pi on the outside. We now can do this integration. Each term is just this anti-power rule. And so x to the 6th becomes 1/7 x to the 7th. Here we get an x to the 4th. We're going to divide by 4, 2 and 4. I can reduce that to a 1/2 x to the 4th. This becomes a 2 divided by 2, so minus 1/2 x squared. Add 1 to this to get 3/2. I'm going to divide by 3/2. This is going to be the trickiest of all this, dividing by this fraction, right? So 3/2 dividing by 3/2 will give me 4/3, so plus 4/3 x to the 3/2. And we're evaluating this from 0 to 1. And as always, beautifully in this case, we have this 0 that we're subtracting. Each term has an x in it. And so when I plug in 0, I don't need to worry about that. I'm subtracting nothing. When I plug a 1 into this is actually really nice how this works out, because in this case, I just get 1s, and 1 to any power is just 1. And so what I get is pi times 1/7 minus 1/2 minus 1/2 plus 4/3. Then all we have left is some fraction work. I won't show that, but when I added these all together, or added and subtracted these together, what I got was 20/42 times this pi right here, which we can reduce down into 10/21 pi. As with all the examples so far, the actual integration work was the easy part. The most difficult part is setting this up. And again, for this example, why it's different than the other examples, because we're not rotating around an axis, we're rotating around this horizontal line y equals 1. And it can be a little bit confusing because then our inner circle isn't just like the square root of x or x cubed. In this case, you really need to analyze the picture and look at, okay, what is then the closest function to y equals 1? Well, that's this green line right here, or the square root of x. So the length of that is the difference between a height of 1 and that square root right there. And then the outer, so that was this part right here. Then the outer radius is the difference between 1 and x cubed, which gave us this outer radius. And again, while most of the focus in our examples have been about these solids of revolution where we're spinning around an axis or these horizontal or vertical lines, the last example that we're going to show you is actually this method of using integration to find volume does not have to be about rotating. We can take many of our basic geometric 3D objects, and as long as we can accurately describe a cross-section, then we can use integration to formulate these formulas for the volumes. All right, in this example, we're being asked to find the volume of a pyramid that has a height of h and a rectangular base of 2b and b. So let's create this object right here so we can visualize what's going on. So we have this rectangular base that has one side that's 2b and one side that's not to b. And then we have this height of h right here that makes this pyramid, and let's see if I can freehand this to make it look somewhat legitimate. That doesn't look that bad. So what we're going to do is our technique. So in this case, we're going to try to find cross-sectional pieces that we can iterate along the height from the bottom to the top. And I'll say this right here, and just in looking at this, I'm looking for a place where I can have these uniformly shaped cross-sectional pieces. And I think the most obvious is to attack this square right here. So as we go up, if we think about some height right here, and we take a cross-section across this right here, this cross-sectional piece will also be a square. We can actually use, in this case, and you've seen this previously, especially in Calculus 1, you probably dealt with this, especially when related rates and other issues like that. What we're geometrically going to do is we can relate the size or the dimensions of this cross-sectional piece right here using similar triangles and the information that we have from these original base and height. Also, I want to say, in order to make this analysis, what I'm going to do is I'm going to think of a triangle that goes right down the middle of this. So it doesn't sit on these slants, but goes right down the middle of this object right here. And I'm going to compare that to find this edge and this edge using these sides and that height and the idea of similar triangles. So first up, I'm looking at this triangle right here. So what I'm looking at is this triangle. It has a base of B right here. It has a height of H. And specifically what I'm going to do is I'm going to use Y to be the height that I go up right here. I know I can go from 0 to H. H is a fixed number in this case. It's a constant for the height of this pyramid. But Y is going to be how high up I am off the ground right here. And so if we look at this, we have this cross-sectional piece. We're just analyzing this edge right here. So that edge, or the width of that rectangular piece, I know that this height right here I'm going to define as Y. First, to make my life a little bit easier, I'm going to give this length that I'm trying to find a value. Let's just call this, let's just call it L, or for length right here. And what I'm doing here is I'm going to compare this triangle right here with the bigger triangle. And that's important. I know they're similar because all their angles must be the same as long as I make this completely horizontal slice that's equal to this. Those angles are the same as that angle, and that's the same angle as the original triangle. And what I know then is that this length compared to this length, it must be equivalent to the ratio of the full height and this length right here. So the heights over the bases must be equal in both of these cases. And so for the big triangle here, the height I have is H, the base here is B. And then for this smaller triangle here, I have this base, which is my variable L right here. And the height, well, in this case, if I go up Y units, I had an entire height of H. This height right here of this smaller triangle would simply be H minus Y. Solving for this L right here, that's the length. I'm describing this in terms of H, Y, and B in this case. And so what I'm going to do is I'll multiply both sides by this L, and then I'll divide by the B, or the H over B. And you can see that what I'll get is this L equals this times the inverse of this. So I'll get B over H times H minus Y. So again, this is the expression in terms of Y, H, and B that gives me this length right here. So I'm just going to label this thing right here so I don't forget it. This is B over H times H minus Y. Again, Y is this height I'm talking about going up and getting this cross-sectional piece. Let's now do exactly the same treatment. It's almost going to be identical. But on this side right here, I'm comparing with this base of 2B. And again, to get things started, I'll give a label here. I'm not sure why I'm using these Greek characters, but it makes you sound smarter. I'm going to use alpha for this length right here, comparing it in exactly the same way. So the original triangles, base and height, actually, I was just thinking this when I did this last one. I made this a little bit more difficult because I put the variable or the measure I'm trying to solve for in the denominator. I'm going to rewrite this. I'm going to put these bases on top just to make my life a little bit easier. So in this case, what I'm going to write is 2b over h. So that ratio must be exactly the same as this base over that height. And again, this base I've written as alpha. And then in the below down here, I've gone up y. It has a total height of h. So this height right here is h minus y again. And then in this case, it's a bit easier because I wrote the variable I'm trying to solve for on top like I should have done in the first example. But I'm just going to multiply both sides by h minus y. So I'll get alpha, or this length right here, is 2b over h times h minus y. So we'll just write that in right here. So 2b over h times h minus y. And as stated, this is the measure of this length right here. And so this is 2b over h times h minus y. So before I jump into the integration, let's just back up and make sure we feel comfortable with this so far. So I have these cross-sectional pieces that are these rectangular pieces that are some ratio of this base right here, depending on how far we've gone up. So we're using this y value, or the height, as we transition up this to that's what we're iterating on. This is going to give us our interval. And importantly too, as you can see from this, the width of each of these cross-sectional pieces will be a delta y. And y, I'm just using this case as a vertical chunk. We obviously haven't projected this onto an axis. We could do that, but in this case, I'm just thinking about this delta y as this thickness, or a difference in height, infinitesimally small once I integrate. My sides of my triangle, or my rectangle here, are related like by this. So what I know then is that the area, this cross-sectional area, since this is simply a rectangle, would be this times this. And so then, now we can use integration to find the formula for the volume of this pyramid given this information. And it's important to just reflect and say this. In this case, we are considering they're given us these b's and the h, so the base and the height, are not allowed to change throughout this problem. And that's a really important thing. I want to reflect on that real fast, because I think at times in calculus, it can start to get confusing about, well, what do we mean by constants and non-constants? The statement is this. If you give me this situation, yes, you can generally say the b value and the h value, but those are not allowed to change throughout the work of finding the volume, right? So as I'm finding the volume, you're like, hey, Mike, I'm changing the base now to 10 and then to 5. Keep on trying to find the volume. That is not fair, right? In this case, we're considering only the fact where as we're doing this work, these b and h values have to be constant. And why I say that is when I go to integrate this, these factors right here are actually constant factors that I can pull out of the integration. So as I write this then, so I have the volume of this figure is the integral from 0, from the bottom of this, to a height of h. And this is important. I'm using y. Y is going to be the height of these cross-sectional, or how far up this cross-sectional piece is. I'm going from the bottom of this pyramid to the top of the pyramid, meaning my y value ranges from 0 at the bottom all the way up to h right here. Again, it's a constant value throughout this problem. I'm going to pull out these constant factors. So I have 2b squared over h squared. So 2b squared over h squared is going to be a constant on the outside. And then I get this h minus y squared dy. And then at this point here, I could obviously expand this h minus y squared. But what I'm going to do is use a u sub here. So let's let u equal h minus y, meaning that du is negative dy. Bring the negative over here. Also, since I'm at it, let me do my change my limits of integration here. So in this case, when y is 0, I get h minus 0 is h. So that's my new lower limit. And then when y equals h equals 0. So interestingly, those limits just change places. So let's make that substitution here. So I got this constant 2b squared over h squared. Now I'm going to switch these, h and 0. Again, based on I plugged in 0, I got out h. I plugged in h, I got out 0. And then now I have u squared du. With that du comes a negative. I'll throw that negative out front there. Now we can integrate, so we have this constant negative 2b squared over h squared, and this, the antiderivative of that, is 1/3 u to the third, and we're integrating again from h to 0. Plugging those in, I get the negative 2b squared over h squared. From this first one, I just get a 0 when I plug in that, and then minus what I get, so I get negative 1/3, plug in at h to get h to the third, meaning that this just becomes the negative h to the third. The negatives will cancel. This b cancels, I get 1, or this h, cancels 2 of these h's down here. And so I'll just have this 3 on the bottom. So if I don't screw this up, I'll make my sign change there. I get 2b squared h over 3. All right, finally, just to put a button on this concept of finding volume by slicing, the really important thing in this case is we're dealing with these two-dimensional objects. In this case, we're looking at the cross-sectional area, the area which is a two-dimensional measure, but we're using that and the concept of integration to measure things that are three-dimensional. That's really, really powerful because two-dimensional work is really simple and we have that locked down on the XY plane. And what we can do now is extrapolate that into the 3D environment. Specifically in this case, what we're doing again is we're focusing on the area of this two-dimensional cross-section, but then saying, well, each one of those has a little bit of width right there. That width, along with the idea of summation, is an important component of the idea of integration. So these ideas marry themselves perfectly. And the final thought is, if you remember when we were talking about the fundamental theorem of calculus, there was this somewhat grandiose statement where it was like, ooh, these moves that only geniuses could do beforehand. I really want to really emphasize this, and hopefully you've had experience with geometric proofs. Geometric proofs of simple two-dimensional shapes are incredibly difficult. If you were to set out to prove the formula for the volume of this pyramid, just using geometry and algebra, this would be extremely difficult. This mechanism of integration is radically powerful. Again, what it's letting us do in this case, it's taking a two-dimensional description and to extrapolate that into the third dimension. And as you might be thinking, there's no reason to limit this to the third dimension. If you have a three-dimensional object, you can use the exact same technique to extrapolate to the fourth dimension and so on.